Okay.
All right, everyone. Following that amazing talk for Professor G, we are on to this afternoon's first panel session. And I guess I'm not the one who made this program, but it turns out I'm the first to give the talk, which is perhaps a little awkward, but I will. Um, and then I will introduce all the other speakers after this. So let me share my screen. One second. Um, And please do keep adding questions to the chat and Discord and through Discord, and we will address all of these after a series of short 10-minute talks. Let's see here. All right. Introducing myself, my name is Kirstin Petersen. I'm a professor in electrical and computer engineering at Cornell University, and I run the Collective Embodied Intelligence Lab. Let me see if I can find my laser pointer here. In my lab, we design and build and operate robot collectives that are inspired by swarms in nature. And we really try to look at a variety of mechanisms and materials, from rigid robots to soft robots to natural swarms, because they all represent, different trade-offs when it comes to collective embodied intelligence. So just to elaborate a bit on our research approach, and hopefully this will also set the tone of the panel a little bit. I think everyone in the audience already appreciates that, if you're trying to design an intelligent robot, then you can do so both through sort of explicit intelligence, like clever algorithms programmed onto whatever computation you have on your robot, or through morphological intelligence, embodied intelligence. We've already heard a lot of good examples, similar to like reflexes in natural organisms, and we'll have more speakers touch on this throughout the afternoon. The point of my lab is that if we don't just have a single robot, but if we also have more robots, then there's a lot more we can do, right? So again, we can sort of take a traditional intelligence approach where we can do careful pre-planning, or we could do, central computation or control, or decentralized control with lots of inter-agent communication in order to produce intelligent behaviors. But we can also, again, take more of the embodied intelligence approach where we can produce coordinated behaviors either through physical interactions between robots, or even by having robots actively modify and sense a collective or a shared environment. I'd say we already, have a lot of knowledge and tools in the bag on the left half design space here, and of course the right half design space is the one that we're really sort of highlighting through this fantastic embodied intelligence conference. So I think it's important that we all appreciate that these tools complement each other, right? It's not that there's a one right answer, but they complement each other. And I think every new challenge we take on requires a dedicated mix of design tools depending on the particular task and the particular robots and the particular environment that those robots are embedded into. So I just want to show you a couple of quick examples of some recent works out of our lab. And this first one is going to be in simulation only. But my point of it is to really try to show the power of letting robot collectives or swarms of these very simple particles couple locally. So what I'm showing you here is a swarmulator particle right here. So a chiral swarmulator is just a particle that rotates around some point in space. It has a phase related to where it is on that circular trajectory, and it can couple both spatially and temporally to nearby particles. So if we put two of these into a simulation framework, they don't do much, they're not that exciting, but when you scale up the numbers, the swarm exhibit much more complex emergent phenomena. And we can, superimpose different means of coordination. So here we added phase coupling, and we can even play around with the swarm composition in terms of their natural frequencies to produce a wealth of emergent behaviors that are much beyond what individuals can achieve, right? And the cool thing is that we start with these super simple particles up here, where you can use first principles to analyze their behavior, but as soon as we scale to larger numbers, right, then these interactions produce these emergent behaviors that are incredibly complex to predict and analyze, but are potentially useful functionalities. And so in this recent paper in Nature Communications, led by Stephen Serron, Dr. Stephen Serron, I should say now, we expanded the original swarmulator model to include a number of these very sort of realistic features that we see throughout real swarmulators. and then making it, so really trying to make it more representative and enable sort of a wealth of new behaviors that we hadn't seen before, including interacting phase waves, organized arrays of vortices, concentric phase oscillation or organization, radial oscillation, and much, much more. So hopefully this example, right, makes you appreciate this powerful approach there is to employing many, many robots or many, many particles to complete a task, more so than just like a traditional single robot system. Okay. So that's like one part of our, design toolbox. We work across the full toolbox here. And so one thing that's perhaps, or an example that's perhaps a little closer to home is one of our recent robots that is based more on morphological intelligence, right? So this idea of building reflex-like behaviors into the body of the robot. So this just came out in Advanced Intelligent Systems. There we are. Cool. These are soft actuators with a single pressure inlet up here. And we're purposefully in these actuators leveraging fluid viscosity to produce pressure distributions throughout the actuator to in turn drive spatial deformations in that actuator. And so you can see that in this video here. If it'll play, hopefully it will. There we go. And so these actuators are just composed of a series of hollow bellows that are arranged in 2 columns around a neutral plane. They're connected together with these thin hollow tubes here. And now simply by changing the inlet pressure profile, we can generate these complex gates where we change both the spatial motion cycle and how quickly it evolves through that space. And so in the paper, we expand on the mechanisms at play and we present a detailed predictive model. And then we use that same model to produce this soft legged walker. And all we're using, right, are 2 simple syringe pumps. And we're just changing the temporal profile of the inlet pressure in order to change these different gates. So long story short, the trick here is that we've carefully chosen the relative timescales between the solid and the fluid and the input pressure cycles in these actuators. And then we let the morphology of the actuator do most of the work for us. So we get out of using, complicated drivers or complicated control circuitry, right? But we actually get to use sort of the continuous space that we get for having infinite degrees of freedom in 2D. So I believe Dr. Yoav Mattia is going to expand on this in a brief talk later in the conference. And I invite you to look at that. To give some examples at the sort of lower right half plane of our toolbox here, this is an example, it's a little bit of an older example, but it's an example of how robots can use their shared environment to coordinate. So these here are construction robots. They're all given a desired blueprint and then pre-compiled traffic rules within that blueprint, as well as some local order restrictions on how to place bricks. But past that, they coordinate solely through the environment. So by that, I mean that every robot here senses only where it is on the structure, what the local configuration of bricks is, but they're not aware of other robots. They don't communicate at all. There's no overall assembly plan, and they're not aware of the state of the structure. And what's happening is that the depositions by every robot in the shared environment prompts particular actions in robots that come by later. And yet we can still sort of give provable guarantees that the system will eventually produce the structure that we want. So this example is a little old by now, but we're actually still finding new insights related to the collective dynamics that slowly trickle out in publications every year. So please do keep an eye on those. In the final example, I just want to give you a quick example of how robots can coordinate through physical interactions. This is a collaboration with the Max Planck Institute for Intelligent Systems, and it came out in Nature Comms last year. And so in this example here, we have 100 microrobots floating on a water-air interface, and the microrobots are just these little discs. They're about 0.5 millimeter in diameter. They're sputter-coated in ferromagnetic materials. So when we subject these disks to 2 global orthogonal time-varying magnetic fields, we can manipulate their local attractive and repulsive forces. So that includes dipole-dipole interactions, hyperdynamic forces, and the capillary forces between them. And what we can do by doing that is produce a range of interesting, emergent, and useful behaviors, ranging from navigation of intricate environments to non-contact based manipulation of objects, or flow-based manipulation of objects to contact-based manipulation of objects. Sorry, so this is the non-contact-based, and this is the contact-based manipulation. So, an example where, there's no sort of explicit intelligence on board every individual robot, but we're using the local physical phenomena to still produce globally useful behaviors. Okay, so I'll end with that. And we have many more projects along these lines. So if you're interested, please do check out our website. And the point of my talk is just really to say that I think we should sort of embrace our knowledge of all of these different tools in the toolbox and really try to tailor, and that there's a lot of strength to tailoring every solution to the particular problem that we have at hand.